بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome back in the general chemistry lectures. Inshallah, today we are keep going in our general chemistry chapters. Inshallah, today I'm going to continue with chapter 11, which is entitled Liquids and Intermolecular Forces. And let me start with sharing with you the file I'm going to work from it. Okay. Okay, this is chapter 11, Liquid and Intermolecular Forces. And inshallah, this was done by me, Mahmoud Abdel-Latif, under the Department of Chemistry, College of Science, United Arab Emirates. And last time we have reached to exactly that figure, this one. Okay, and I told you that for the non-polar series, the trend is normal. Okay, increasing the molecular weight, increasing the boiling point, while going to the group 5 and the group 6 and the group 7, the trend is normal till you go to the smallest molecule, and strong anomalous happens by increasing the boiling point. It should be decreased according to the molecular weight, but actually this kind of, the smaller molecules are highly polar compounds, because it contains oxygen and fluorine and nitrogen, which they are the more electronegative atoms. So it's the dipole moment is the more predominant for this one, and it is the reason for increasing the boiling point. Okay, and now let us start with the last one. We have discussed together three types of the intermolecular force: the London force, and dipole-dipole interaction, and ion-dipole interaction, and the last one is hydrogen bonding. Okay. Okay, hydrogen bonding, just let me tell you something. Actually, hydrogen bonding is dipole-dipole interaction. If you take, for example, the water, okay, if it's something like this one, let me write it something like that one, and it's a polar compound. As you know, it's partially negative, as you know, and partially positive, and if you have another molecule here, okay, this is partially negative, there is electrostatic attraction between the partially positive and partially negative oxygen, and this is called dipole-dipole interaction. Once the dipole-dipole interaction is once a hydrogen is involved in the dipole-dipole interaction, when it's connecting to oxygen or nitrogen or fluorine, this kind of dipole-dipole is called the hydrogen bonding. It's called the hydrogen bonding. So the hydrogen bonding arises in the polar compound also, and the hydrogen bonding is definition electrostatic attraction between hydrogen and the more electronegative atom like oxygen or nitrogen or fluorine and so on. And by the way, the hydrogen which which connected to the oxygen, it should be on some more electronegative atom also. It could be on oxygen, it could be in nitrogen, it could be in, and so on, in sulfur. Okay, so just reminding you, this is intramolecular force and this is intermolecular force. Okay, so the dipole-dipole interaction experienced when hydrogen bonded to nitrogen or oxygen or fluorine are unusually strong. It's very, very strong. We call this kind of interaction hydrogen-hydrogen bonding. Okay, if you look to these molecules, these are polar groups or polar compounds. As you see, there is a dipole moment, which is a vector quantity, which is directed to the direction. Okay, it's direction to in the same direction of the polling electrons, as you see, by the more electronegative atom. Okay, if you look to that one, okay, this is intramolecular hydrogen bond. Okay, It's a covalent bond between hydrogen and oxygen. And that one, the dotted red line is intermolecular hydrogen bonding, intermolecular force, which we call it hydrogen bonding, okay? Which formed between, okay, hydrogen and more electronegative atom oxygen or fluorine or nitrogen, as you see. And just keep in mind that these all hydrogen, before forming the hydrogen bonding, should be connected with intramolecular bond with any of more electronegative atoms like oxygen, like fluorine, like nitrogen, and so on. Okay, so this kind of dipole is called hydrogen bonding, which involves the electrostatic attraction between the hydrogen and the more electronegative atom like nitrogen, like sulfur, fluorine, and nitrogen. Okay. Hydrogen bonding arises apart from high electronegativity, as I've already told you, electronegativity of nitrogen or oxygen or fluorine. Okay, if you look to this figure, okay, actually the hydrogen bonding distance between this hydrogen and between this oxygen, it's ranging from, for example, 1.8, so to say, till 2.4, 2.6. Okay, actually, inshallah, you will, the person who will going to do some research, he will find that there are 3 types of the hydrogen bonding, okay, and they are divided into strong and weak and medium. And the strong one, okay, which has a lower distance, okay, and also the heavy distance between the 2 oxygen, it's called the heavy distance, also the smallest one, say to say, okay. So actually hydrogen bonding are responsible for many properties of water and of materials, like the boiling point and so on. We will discuss that later, okay. So just this is water molecules, and the red dotted line are the hydrogen bonding, okay. Also, when hydrogen is bonded to one of those very electronegative atoms, the hydrogen nucleus is exposed to form the hydrogen bonding, okay. This is many example. This is again the water molecules, as you see, okay. And the dotted, this kind of dotted lines are the dipole interaction between the partially negative and the partially positive charge. And once it involves once any of these electrostatic attraction involves hydrogen with more electronegative atom, it's called the hydrogen bonding, like in water, like in ammonia, okay, like in hydrofluoric acid, as you see, okay. Also the same, this is hydrogen bonding, okay, and this is also hydrogen bonding between hydrogen and nitrogen atom. Okay, hydrogen bonding are responsible for many properties of the substance. For example, boiling point and melting point and surface tension and vapor pressure. And I'm going to discuss here, for example, okay, ice is floating. Okay, this is anomalous behavior for the condensed matter. Okay, if you're going from liquid, okay, to solid, in general, okay, in general, this is more dense substance. The solid, the intermolecular distance between molecules is smaller than the intermolecular distance in case of liquid. So the volume here is bigger than the volume here. And as you know, density is defined by mass per unit volume. So once the volume is decreased, the density increases. So thus, in general, the solid is more dense than liquid, and the opposite is happening in water. The ice is less dense than liquid water. Subhanallah. Okay. If the opposite is happens, all the living organisms in the sea and the oceans, okay, will die if the ice were more dense than liquid, okay. So solid are usually more closely packed than liquids, okay. As a result, therefore, solids are more dense than liquids. Ice, in case of the ice and water, it's opposite. Ice is ordered with an open structure to optimize the hydrogen bonding, which is responsible for this anomalous. Okay, therefore the ice is less dense than water. Okay, so the main reason, the very strong reason for the ice to be floating over the water, like here, say to say, okay, is the hydrogen bonding. Just if you had optimizing the structure, if you have and optimize the hydrogen bonding, as you see in open structure, okay, it arrange it in a way that increase the volume of the ice, and as a result, the density, okay, decreases because density is inversely proportional to the volume. Okay, that's great. So floating of ice in the surface of liquid, the main reason for that is the hydrogen bonding, which, okay. Just summarizing the intermolecular forces, we have, okay, 4 intermolecular forces, and if you would like to arrange them according to increasing of energy, or according to the increasing the strength, say to say, comes in the first one, London, okay, and then after London comes the dipole, and after that comes hydrogen bonding, which is stronger than the dipole, and the most strong one at the ion-dipole interaction. Okay, how did you know the type of the intermolecular forces? Okay, as you know, this one depends on the number of electrons, so it depends on the molecular weight, so it's found in all compounds. Okay, dipole for the compounds which have permanent dipole moment. Hydrogen bonding, it's dipole-dipole interaction, but this kind of interaction involves the electrostatic attraction of hydrogen to more electronegative atoms like oxygen, fluorine, nitrogen, and the ion dipole, something like solvation of sodium chloride in NaCl. Okay, how did you know which is which? Is that how did you know the type of the intermolecular forces? Just ask yourself a question: are the mixture you have, say to say, contain ions? Are ions present in this mixture? If yes, you have two possibilities. It could be ionic or it could be ion dipole. Okay, just ask yourself another question: are a polar compound are present like water, say to say, okay, in the presence of sodium chloride? Okay, if ions are present and polar compound are present, so it's an ion dipole interaction. So if it's yes, you have ion dipole force or ion dipole interaction like NaCl and water. Okay, if you have only ions are found without any any polar molecules, okay, so you could expect the ionic compound. You could expect ionic bonding like NaCl, for example, ammonium nitrate, potassium, bromide, potassium, fluoride. So it's ionic. Okay. So you ask yourself in the first question: are ions are present? If it's yes, it could be ionic or ionic bonding, ion dipole or ionic bonding. Okay. If ions are not found, okay, just you have two possibilities. It could be polar and it could be non-polar. Polar or non-polar? Non-polar. Just ask yourself: are polar molecules are present? If it's no, so you have London force. You have dispersion London force. If the polar, if you have the polar molecules in your mixture, if it's yes, you could expect that you have dipole-dipole interaction. Okay, dipole-dipole force. Okay, actually these three are called van der Waals forces, and okay, And as you see, going in this direction, increasing the interaction strength. As I told you, the weakest one is dispersion force, and then the more stronger dipole-dipole, more stronger hydrogen bonding. Strongest is the ion-dipole forces, ion-dipole force, as you see. Okay, as I have already told you in that chapter many times, that intermolecular forces affect many physical properties, many physical properties, like the vapor pressure, melting point, boiling point, and surface tension. Okay, actually, if you look to these two examples, this is okay, acetic acid, and this is 1, 2, 3. It's a propanol, okay, propanol or propyl alcohol. Okay, normal propyl alcohol, the common one, or propanol, the IUPAC name. Okay, as you see, this one can form two hydrogen bonding between the molecules. While here, it's only one hydrogen bond that can form it between the molecules. So what do you expect? You expect, of course, the increasing the number of hydrogen bonding, increasing the intermolecular force, increasing the hydrogen bonding strength. Okay, so you need more energy to break them. So the boiling point increases. Okay, if you look here, acetic, the molecular weight is 60, and also the molecular weight is 60 here. But here you have two hydrogen bonding. Here it's have only one hydrogen bonding. You could expect that the boiling point here it's higher than that one, and it's clear. Okay. So each molecule can form two hydrogen bonding with the neighbors, but here each molecule can form just only one hydrogen bonding with the neighboring molecule. The strength of attraction between the particles can greatly affected by the properties of the substance of solution. Okay, the strength of attraction between particles or between molecules can greatly affect, of course, its controls, or can greatly control the properties of substance or solution, like as I mentioned, the boiling point and the melting point and so on. Okay, as an example for the effect of the hydrogen bonding for the vitamin soluble vitamins, water soluble vitamins, and water insoluble and water in soluble vitamins. How? Okay. If you look to vitamin C, it's a very famous vitamin. We always use it in everyday life, okay, in lemon or orange and so on, okay. Okay, if you look here, you find many OH group which can form many hydrogen bonding. So when you dissolve this compound in water, it forms with water many hydrogen bonding. That's why it's soluble. And at the end of the day, it's a soluble vitamin. Okay. If you go to this vitamin E, okay, there is no, okay, just it's it's a strong chain without any OH. You have only this one, okay, and this is not enough to dissolve with the whole or the higher molecular weight compound in water. So if it forms hydrogen bond, just only form one hydrogen bond. And if you see here, the molecular weight is very high, as you see. Okay, so this OH is not enough to be soluble in water. That's why it's water insoluble vitamin. Okay, that's great. We are going to discuss some selected properties of liquid which depend mainly on the intermolecular forces. We are going to discuss viscosity and surface tension and the capillary action. Okay. Okay. Question: why, if you look to the honey, okay, it's dripping in that way, while water it has drops like that way. Okay. So what's the reason for that? Actually, the reason for that is the viscosity. Okay, viscosity. Okay. Why the difference between honey dripping and the water drops? The main difference here, or the main reason for that here, is the viscosity. Okay, viscosity It's defined by the resistance of liquid to flow. Okay, resistance of liquid to flow. It's called viscosity. It's related to the ease with which molecules can move past each other. Actually, viscosity increases with a stronger intermolecular forces. And the intermolecular forces, you could imagine here the intermolecular forces between the honey molecules. It's very strong comparing to the intermolecular forces between the water molecules. Okay, it depends on the molecular weight. So viscosity depends on two factors: intermolecular forces, okay, and temperature. It's directly proportional to the intermolecular force and inversely proportional to the temperature. Increasing the temperature decrease the viscosity. If you look to that compound, they are non-polar compounds: hexane, heptane, octane, nonane, decane. Going from up to down, the molecular weight increases. Okay, as you see, the length of the chain increases, so the molecular weight increases. It's non-polar, so the only intermolecular force here are dispersion force or London dispersion forces. So which increasing by increasing the molecular weight. Once the molecular weight increasing, the London force increasing, you could say here the viscosity increasing. 3 point, okay, 3, 4, 5, 7 times 10 to the power minus 4, and then increase to 1 times 10 to the minus 3. Okay, so how can you explain the following? Okay, how do we explain, or how can you explain this behavior? Okay, you could see some insects can stand in the surface of the water without sinking in it, without going into the pulp. Also, you could put a small nail from the iron in the surface of water. Even the density of iron is very, it's greater than the water. And why that happen? Why does that happen? The main reason for that is the surface tension. Okay, we are going to discuss another property which depends mainly on the intermolecular force. It's called surface tension. Okay. Okay, surface tension results from a net inward force experienced by molecules on the surface of the liquid. How we can explain that? How can I explain that? Just look to two molecules, one in the bulk of the molecule, that one, so to say, and if you look to it, the net force on that molecule, which I put the pin on it, equal to 0. Why? Because if this molecule pull in this direction, it's cancelled by the other one in the other direction. So it's this molecule surrounded from all directions by molecules, so it's in equilibrium. Okay, the net force on it is 0. Okay, while if you look to a molecule in the surface like this one, it's not in an equilibrium. It's not okay. The net force does not equal to 0. Why? Because they have downward molecules which pull it downwards, and there is no any molecule walls, no upward molecules that balance the pulling in the bulk. So you could expect that the surface molecules of the liquid, this will be pulled down by the force, okay, pulled down to the bulk of solution. This is surface tension. Okay, on any surface molecule there is no upward forces to cancel the downward forces, which means each surface molecule feels in it downward pull. Okay, while on any interior molecule or any molecule in the bulk, each force is balanced, okay, by a force pulling in opposite directions, which means that interior molecules feel no net pull in any direction. Okay, that's what we call it surface tension, which is responsible for many properties like that I'm going to discuss. Okay, now we are 37. Are you there? Sir Ahmed Yusuf, you still with me? جزاكم الله خير ابو حميد. ماجد بي مصبح اللي دايما ليفت اس جوين اند ليفت اس. ماجد. ماريا. ماريا خليكم شاهدين يا شباب اهو. مانج علي. هلو. وديمه. مس وديمه. مس وديمه. خليك شاهد ابو حميد. خليك شاهد يا احمد بي يوسف عشان الناس بتزعل بس. اوكي يكفيني يا ابو حميد انت والناس اللي معاك يعني معايا. اوكي. Okay, surface tension and the meniscus and the capillary action. What's the meniscus? Meniscus is the shape of the surface of the liquid. It could be in as U shape, okay, or it could be any shape with convex and concave and the convex shape of the surface of the liquid. It's called the meniscus, okay? It's called the meniscus. Okay, meniscus is the shape of the liquid surface, okay? Okay, the behavior of the liquid in the capillary tubes, okay, in order to explain it, we have to discuss, we have to expose to two forces, which are cohesive forces and adhesive forces, or the responsible for the meniscus to be in that one, or in that one are two forces, the cohesive forces and adhesive forces. Adhesive are the attraction between the liquid and the solid, okay? Adhesive forces bind the molecules to the surface, while cohesive force, the attraction force between the same molecules. Cohesive forces bind the molecules to each other, okay? So if there are a competition between these two forces, cohesive and adhesive, if the adhesive force are bigger than, you end up with A shape. If the cohesive force are bigger than the adhesive one, you end up with the P shape, okay? Which is N, and this is which is U. Let's see. If adhesive forces are greater than the cohesive, so the liquid surface is attracted to the container more than the bulk molecules, and at the end of the day, the meniscus is U-shaped, like water in glass, like water in glass capillary tube. The other way around, okay, if the cohesive force, or the opposite, if the cohesive forces are greater than adhesive forces, the meniscus is like in B, okay, like is curved downward. Here it's curved upward, here it's curved downward, okay, like mercury in glass, okay, like in the capillary shown in figure B. Okay, and this is something like rail, for example. This is the surface of water in capillary, in test tube, so to say, or capillary tube, and this is the surface of mercury, okay, in glass. As you see, it's U shape, and here you could say it's N shape, so to say, or curved upward, curved downward. Okay, if you look to this is water molecule, bulk of the, okay, they are connected with the hydrogen bonding, as you see, okay, and you could see that this is the glass wall or tube wall. It's connected by adhesive forces. This is the adhesive force, okay, see, it's adhesive force, while this is a cohesive force, okay. So you see, if the adhesive is large, greater than cohesive, you will find the shape of the water like this one, okay. While in the mercury in glass, okay, the cohesive between metal atoms are stronger than the adhesive between this one and this one, so it takes that shape, as you know. Okay, so this is, as you see, mercury cohesive force, as you see. Okay, here, because the adhesive force is greater than the cohesive water molecule touching glass adhere to the wall more than the bulk, okay, and forming concave surface. Concave surface, this one, U shape, okay. Because cohesive is greater than adhesive in case of mercury in glass, okay, so mercury molecule touching glass adhere to the wall less than to each other, forming convex surface. Okay, that's great. Now let us go to the vapor pressure. Okay, if you have a container, say to say, of liquid, okay, and you have, it's a half, say to say, liquid, as you see. Okay, actually the particles of liquid are in random motion, okay, and there are average kinetic energy. Some molecules are faster than the other. The faster molecules can escape to the evacuated space above the liquid and form vapors. You could see some surface molecules are vaporized, okay, and this kind of vapor exert a pressure on the surface of the liquid, okay. In the beginning of the evaporization, the rate of evaporization is decreased and increasing with time. At some time, some vapors, okay, molecules will condense and be back and return back again to the liquid, okay. At certain time, the rate of vaporization is equal to the rate of condensation. At that point, dynamical equilibrium is reached, okay, and the area above the liquid is saturated with the vapor, so, and it exerted the pressure on the liquid, and this pressure is called the vapor pressure, okay. Be with me, just read with me this kind of things, okay. At any temperature, some molecules in a liquid have enough energy to escape, to break free, to escape, okay, to overcome the surface and go to the evacuated above the liquid. As the temperature rises, okay, the fraction of the molecule that evaporize increasing. As the temperature rises, the fraction of the molecules that have enough energy to break increase, okay. This is already the shape I have already explained to you, okay. This is liquid and some molecules evaporates these, okay, and at some times some molecules are condensed again, okay, and return back to the liquid like that one. At certain point, the rate of vaporization is equal to the rate of condensation. At that point, the dynamical equilibrium is reached, okay, and the area above the liquid is saturated with the vapor, and this vapor exerts a pressure which is called the vapor pressure, okay. Increasing the temperature will increase the number of molecules that escape to the space, okay. If you look to the blue curve, this is the y-axis number of molecules, and this average kinetic energy or kinetic energy. If you look to the blue curve, okay, suppose this is the minimum kinetic energy to escape. Okay, the minimum kinetic energy for the particle to have to escape to vapor, minimum kinetic energy are needed to escape, okay. So if you look to the blue curve, the area under the blue curve here is the number of molecules, okay, that can escape, okay. Raising temperature, if you raise the temperature, the red one, higher temperature, the area under the red, this red, and in addition to the blue one, are the number of particles or number of molecules that can escape it, increased by increasing the temperature. So increasing the temperature, increasing the number of molecules that can escape to form a vapor. Okay, just blue area, number of molecules having enough energy to evaporate at lower temperature. Red and the blue, okay, the whole area here, the number of molecules having enough energy to escape or to evaporate at higher temperature. At higher temperature. Somebody is writing to me something. I don't know. Okay. Like water in a bottle. What do you mean, Mr. Ahmed?
Doctor, if you open a bottle of water and then close it again and put it out at the time, you will see evaporation on it. Then
right, all right.
Yeah.
Right. Thank you, Mr. Ahmed. Agree with you. Thank you so much for your cooperation. Okay. For your contribution also. Thank you so much. أحسن أبو حميد. ربنا يحفظك. Okay, great. Okay. Okay, vapor, we're still discussing vapor pressure. If you have a glass vessel like this one, evacuated flask, okay, the pressure is 0 here, no, nothing here, okay? I just allow to the liquid ethanol to be inside, okay? In the beginning of, okay, few molecules are escaped to that space to form a vapor, okay? And at some time, system comes to the equilibrium. Here, pressure is 0. Here, the rate of evaporization, just we have only evaporization, molecule begin to evaporize, pressure above this liquid increase. Molecules leave and enter liquid at equal rates. Okay, at some times you reach the dynamical equilibrium. Okay, you have two processes, evaporization and condensation, and both have the same rates. Okay, molecules leave and enter the liquid at equal rates. Pressure reaches to a steady state. Okay, this area is saturated with the vapor, so the pressure becomes constant, and it's called vapor pressure. Okay, P means equilibrium. P means equilibrium. Okay, it's not P. I mean pressure equal to the equilibrium vapor pressure. So, and here the pressure increases. Okay, in the beginning. As more molecules escape to the liquid, the pressure they exert increases. Okay. Again, the liquid and the vapor reach a state of dynamical equilibrium at which the rate of condensation equal to the rate of evaporization. Okay, at the same rate. Okay, this we have already discussed. Just see this one. In the beginning, okay, you have the whole space, and some molecules evaporize. Okay, evaporization only. Okay, and then at sometimes some molecules starts to condense again to return back to the liquid. Is still the rate of evaporization greater than the rate of condensation. At the dynamical equilibrium, the rate of evaporization equal to the rate of condensation, and at that the area above the liquid is saturated with vapor and the pressure is constant, and it's called vapor pressure. Okay, vapor pressure. Okay, and now let us discuss the boiling point. Boiling point is related to the vapor pressure. Okay, actually the boiling point is the temperature at which the vapor pressure of the liquid equal to the atmospheric pressure. Okay, the boiling point of a liquid is the temperature at which its vapor pressure equals to the atmospheric pressure. Equals to the atmospheric pressure. Okay, which is 762 or mercury millimeter. Okay, the normal boiling point. Okay, normal boiling point is the temperature at which the vapor pressure is this value. Okay, the normal The normal boiling point is the temperature in which the vapor pressure equal to that one. How we can determine the boiling point? Okay, just you draw a curve or a relation between the temperature and the vapor pressure. Increasing the temperature will increase the vapor pressure, okay, and so on. And just draw these lines, and at atmospheric pressure, okay, just draw a line parallel to the temperature axis, as you see, okay. This one will be the normal boiling point for diethyl ether. You can get it just from the from just extrapolation, right? Draw a line parallel to the y-axis to intersect. Okay, it will be that one. Okay, 27. I'm sorry, 34. And this is for ethyl alcohol. Also, if you go down, you will end up here something like 70 something, 78. For water, it's 100, as you see, 100 Celsius. This is the normal boiling point at atmospheric, when the vapor pressure equal to 1 atmosphere. Okay. Actually, the boiling point depends, as I mentioned, on the vapor pressure. If the vapor pressure above the solvent, above the liquid decreases, the boiling point decreases. If the vapor pressure above the liquid increases, the boiling point increases. Do you know the mechanism of the pressure cooking band, so to say? Okay, it depends on the vapor pressure, which in all your kitchens. Okay, it's used for cooking fast food, and the mechanism is that, okay, it's designed to be closed, and the vapor pressure inside it increases, so it makes the water, so to say, boil at higher higher temperature than 100, of course, because the vapor pressure increases more than 1 atmosphere. So the food is cooked very, very fast. Okay, that's great. Okay, with this figure, I think I finished the chapter 11 and the general chemistry 1. And this is some small practices, okay, and I'm going to tell you what, inshallah, we are going to do in the next lectures till the final exam, inshallah. Which forces below the strongest intermolecular forces? Okay, it's ion-dipole interaction. I have already told you that, okay, this is number 1, okay, and this is number 2, and this is number 3, and this is the number 4, the last one. So the right answer here is ion-dipole forces. Okay. Name the intermolecular interactions below. Okay, just I'm giving you some molecules and which could contain intermolecular forces, and you could. Okay, as you know, London force are found in all compounds, because it depends on the number of electrons in the molecular weight. Okay, just this is fluorine, okay, and this is hydrogen from this chart. So it's a dipole interaction. Once it contains hydrogen, it's a hydrogen bonding. This is hydrogen bonding, okay. This is sodium, okay, and this oxygen with water. So it's an ion with a polar compound, ion-dipole interaction, ion-dipole interaction, ion-dipole interaction, okay? This is fluorine, F2 with F2, okay? This non-polar compound, so it contains only London dispersion, If you look to that one, this is sulfur with oxygen, sulfur with oxygen. These are polar compounds. You could expect it contains the dipole interaction, okay, which will have the higher viscosity, this one or this one, okay. Okay, this is glycerol, I think, and this is propanol. If they have the molecular weight the same, Okay, this contains 3 OH groups. So you could imagine that there are 3 hydrogen bonding will form it between the molecules, and this contains just only 1 H group. So 1 hydrogen bonding will form. So the viscosity increases with the increasing the intermolecular forces, which is hydrogen bonding here. So this one will be bigger than propanol. Okay. Explain the difference in boiling point below. You have these two. Okay. This one is higher than this one. Why? Even the molecular weight, although the molecular weight are the same, because there are 2 hydrogen bonding between the molecules, and here just only 1 hydrogen bonding can form between the molecules. Okay. Explain the difference in the boiling point below. Okay. This is can form hydrogen bonding. It contains the hydrogen with the oxygen. This is polar. It contains the dipole-dipole interaction, and this is hydrogen bonding. So you could expect that higher hydrogen bonding than this one. Okay. Propanol has hydrogen bonding. In addition to the London force, which is found in all compounds, while ethyl methyl ether has just only dipole-dipole interaction. In addition to the London one, hydrogen bonding is much more stronger than the dipole-dipole interaction, as I already told you. Which force below increase? Okay, which forces below increase in strength as the molecular weight, okay, of the compound increase? Which intermolecular force depend on the molecular weight? It's London dispersion force. London dispersion force. What is it? London dispersion force. Okay, that's it. Okay, which compound below is not capable of forming hydrogen bonding? Okay, the hydrogen bonding is formed between hydrogen and any of it: oxygen, fluorine, nitrogen. Okay, so here it can form. Here it can form. Here it can form hydrogen bonding. So the right one is methane, which is non-polar compound. Okay, which compound below had the highest boiling point? Do you remember this? The figure I have started with you today. Okay, the trend was in that one. Okay, okay, and this was H2S, and this I think was H2, I think selenium, something like this one, and there's another one here, and the hydrogen. The H2, it has anomalous. Okay, its boiling point, it's very high comparing to this one. According to the molecular weight, okay, this trend it's okay, increasing the boiling point. While the smallest molecule, it contains hydrogen bonding, which is very strong intermolecular forces, and that is the reason for H2O2P has the higher boiling point. Okay, great. Which element below has the highest boiling point? Once they are non-polar, the molecular weight, the higher molecular weight will be the higher boiling point. Okay. I'm sorry. The resistance of liquid to flow is called the viscosity. Okay. It's called the viscosity. The energy required to cause a liquid to boil is called boiling point. Okay. At high altitude. Okay. When you're going up to a higher altitude, the pressure. Okay, I'm asking the boiling point of water decrease or increase? As we mentioned, the boiling point in the vapor pressure above the liquid molecules. Okay, the vapor pressure increases, the boiling point increases. The vapor pressure decreases, the boiling point decreases. When you go to the upper altitude, okay, the pressure decreases. Okay, the pressure decreases above the surface of the liquid you have, so the boiling point should decrease less than 100. Okay, the normal boiling point of water is 100, so it should be decreased less than that one. Okay, these two examples, just they are already solved. Just see them, and if you find any problem, just contact me. Just I'm going to explain this figure to you. Use this figure, estimate the boiling point of diethyl ether under this one. Where is diethyl ether? Diethyl ether, that one. You want the boiling point of that one at that pressure. Okay, we have already, this is the normal boiling point at 1 atmosphere. I'm asking to get this boiling at a pressure lower than 1 atmosphere. Just we should multiply this one with 760 to convert it to Tour. Okay, to know here, for example, you end up with 710. So at 710, say it's here, for example. So you draw a line parallel to the x-axis, and at that point, it's the boiling point at that pressure. How you can get it? Just from this one, write a line to intersect the temperature. It will be that one. Okay, it will be that one. You could expect it should be lower than this one because the pressure is decreased. Okay. What is the predominant intermolecular force in that one? That one, it's a non-polar, so it's a London force. So it's a London force, London dispersion force. Hello.
دكتور سامحني بس على المقاطعة، بس دكتور عادي أطلع لأن عندي موعد في المستشفى بعد يمكن 20 دقيقة.
مين اللي بيتكلم؟ محمد مين؟
محمد النعيمي.
محمد النعيم؟
نعم.
اوكي خلي اوكي فكرني يا احمد يا يوسف. اوكي ماشي يا محمد.
بكتب في الشات يا دكتور.
اوكي انا مش هبص في الشات، ان شاء الله حد بيفكرني ان شاء الله.
ان شاء الله. يعطيك العافية دكتور، شكرا.
اوكي يا حبيبي، لو انت هتبقى ستيل معاه وتكتب اوكي ماشي. اوكي جو اهيد. Go ahead. So, which of the following exhibits dipole-dipole interaction? I doubt about this one. I'm going to skip it, actually. I don't know why. Okay. One of the following substance has the highest boiling point. Okay, which one? It should be which contain hydrogen bonding. This one, it's right. This is wrong. It's solved wrong. Who is writing to me? I don't know.
أنا دكتور okay. بس هذا يقول.
Okay. So it should be this molecule, which contains, it's higher than this one, contains just only one OH. Here it's two hydrogen bonding, here it's one hydrogen bonding. Okay. Which one of the following derivative of ethane has the highest boiling point? Okay, depends on the molecular weight. It should be that one, because iodine is higher than chlorine, higher than bromine, higher than, and so on. So this is the right one. Okay, here it's solved wrong. Okay, great. الحمد لله رب العالمين، الحمد لله الذي تتم بنعمته الصالحات. اوكي، جزاكم الله خيرا يا شباب على حسن المتابعة والاستماع. جزاكم الله خيرا. ان شاء الله يعني اراكم دائما على خير. السلام